So when I was asked to give a title to this talk, I rather foolishly went big with energy security and net zero by 2050. Can we get there? And is the hydrogen economy the answer? As a result, I'm going to be giving quite a broad brush overview. And I'm very pleased that Roger Cashmore's in the audience, because anything about nuclear we can ask him. So which is the bit that I'm glossing over, just to pre-warn you. But what I'll try and do in this talk is not obey Betteridge's law. I don't know if you're familiar with Betteridge's law, but it's essentially the law that if a headline to a newspaper article is a question, then the answer is always no. So can we get there? And is the hydrogen economy the answer? The answer is not no for this, but it's not yes, it's easy. So with that, I'll crack on. Okay, just to say a little bit, I'm sure lots of you on the call know about this already, but I'm from Science and Technology Facilities Council, which is just 15 miles south of Oxford. And we're part of the Harwell cluster, and Science and Technology Facilities Council follows this kind of, the Rutherford-Appleton site follows this kind of boundary here, with the diamond light source synchrotron, which is the bit this kind of snazzy building you can see if you drive down the A34. But tucked away behind, this is a great big mound. It's tucked away as the ISIS neutron and muon source. And we do actually have I'll come back to it at the end, a green ammonia demonstrator right at the edge of site. On this side of site, there's a security fence goes down here, and there's the Harwell nuclear site. And just out of shot, there are two now defunct research reactors, Pluto and Dido, which were built in the 50s and began being decommissioned in the 90s. Okay, this is the view of ISIS looking out towards the Ridgeway. It was also taken on in the middle of a heat wave, because the fields are normally a bit greener than that. And just to give you a little idea of vaguely what the lie of the land is, this building here contains a linear accelerator. We take hydrogen ions or hydrides, H-, and accelerate them before they're injected into this ring under a mound here, which is another synchrotron, but in fact it's a proton synchrotron. And this accelerates protons up to 80% the speed of light at 50 times a second when it's working. And 4 out of 5 pulses go into this target station here, this big building, and there's a heavy metal block about the size of a breeze block, roughly. And neutrons are essentially boiled off and go off in all kind of directions. And there are many instruments do scientific and engineering experiments on. And 1 out of 5 goes to this target station, Target Station 2, which was opened in 2007. And you'll see that this is bigger. And it's not just because it's newer, but it's because this target station uses neutrons with longer wavelengths. That means longer times, and it's used for larger problems. So whereas in this target station we look at the atomic structure, this target station we're looking at, I guess, the mesostructure, as it's called, a kind of structure of small porous things and soap films, things of that order. I'll kind of come back to that at the end. Only to say that when ISIS is on, it takes a large amount of power to get it going and to keep it going, on the order of 10 megawatts. I'll go through what that means in a moment. So just to say, the aims of this talk are to provide an overview of just how big the problem is with energy. And really, is there any way we can solve it? What could we do? What should we do? And I was going to put down as a third thing, of what can we do as individuals? but hopefully that'll become apparent as we go on. Okay, a quick aside: power versus energy. It's kind of going back to O-level or GCSE physics, really, but it's something, unfortunately, that people get wrong all the time, and it's very confusing. And I'm giving an example up here. This was in my latest edition of Chemistry World, which is the Royal Society of Chemistry's magazine. It says the country will need energy storage. Oh, I can't actually see that. Zoom's got a thing. Supplying 50 gigawatts by 2050. Now, unfortunately, 50 gigawatts is not a measure of energy. It is a measure of power. The power is the rate of energy transfer, and it's measured in watts. Energy can be thought of as how long something can keep going at a constant power, measured in joules, but more intuitively watt hours or kilowatt hours. So the UK electricity demand is roughly 1 terawatt hour per day. Now, I've got a bike here because this is my little illustration of why power is different to energy. So I cycle to and from work, which is about a distance of 10 miles. And yesterday, having done some home repairs on my bike, I experienced a chain coming off as I was cycling through the centre of Abingdon, where I live, which caused me to fling forward. And normally, when I'm stopping on a bike, the power is small as I put on the brakes. So the rate of energy transfer is small, and I come to a kind of neatish stop. I won't say elegant, but neatish. This time, however, I was kind of flung forward, and if you've ever seen a picture of Chris Froome, the cyclist, going downhill, it was like that, apart from my feet were not on the cycle dials, on the pedals, and I went head first into the side of a stationary bus, which was extremely embarrassing and very gratifying for a small child who was sat there. As a result, the power, the rate of energy transfer there, as my kinetic energy transferred into my head, was rather more than I was hoping for. So that's what power is. Power is energy transfer. Unfortunately, people use power to mean energy and vice versa. I will endeavor throughout this talk to be very consistent. Do pick me up on it if I'm not. Okay, where is our energy coming from at the moment? And I'm talking on a national level, as I will be for most of this talk. Okay, I was going to make these graphs from the raw data, but Grant Wilson at the University of Birmingham has done an absolutely stellar job of plotting all of this data. And he makes the slides available for free under a Creative Commons license. And so anyone can go out and check out the data and look at them. You just need to, if you search for Grant Wilson on Twitter, that's all he talks about. It's a brilliant resource. So just to acknowledge the work that he's put into this. Electricity generation has actually been a remarkable success story in general terms over the last decade or so. If you think in terms of reducing our carbon footprint, you think coal has roughly double the carbon cost of natural gas. So we've essentially squeezed, I say we, it's nothing to do with me, of course, as a country, we have squeezed coal almost entirely out of electricity generation, which is a really good thing. And natural gas has actually stayed remarkably flat over the course of that time. Wind has been a huge success story. This little yellow band is solar. There's lots of solar farms around me, but it doesn't make a huge portion. Nuclear has been slowly compressed as they eke out every last hour possible out of the old power stations. And obviously we've got a delay before new ones come online. Biomass, that's essentially wood pellets for the Drax power station in Yorkshire. And there's a couple of other minor bits and pieces, pumped hydro and hydro. And there's net imports, and those are interconnects, these high voltage direct current power lines, and mostly that's been from France. But France, unfortunately, also has a very aging nuclear fleet, which has served it very well. But as a result, net imports directly for electricity are going down over the last few years. There is, however, a bit of a problem, although which is not shown in this former graph, where you see wind and solar and it all looks very merry. There's a big problem with renewables. And the big problem, I'm sure you can see here, is that this green line, which is kind of half an hour data, or daily data, sorry, plotted over the last, well, the 3 years between 2018 and October 2021, kind of goes up and down an awful lot. Now, there is a baseline. You can see it's not at zero, the baseline for this green. But that's because it includes biomass, which is the wood pellets from Drax. And it's, I would say fairly arguable whether that really is a low carbon source of electricity, despite all of the claims of Drax. And here's our electrical demand going up and down daily. And you can see the electrical demand, electricity demand, kind of follows a seasonal course of things, but it's relatively flat. That's essentially electrical heating that means it's that shape. So there's a big problem with renewables. You can see these, I've not used, well, Grant Wilson has not used the rest of this scale. That's because there's going to be bigger things coming in, just to pre-warn you. And here they are. Electricity is not all of our energy requirements, and not by an awfully long way. In fact, it's about 1/6 of our energy requirements as a country. And that's as a country with not, unfortunately anymore, a very large manufacturing base either. So here's electricity demand. This is demand for liquid fuels for transport. And you can see where the first lockdown happened. And then there's another lockdown, second lockdown, back in the times of COVID lockdowns. And that has now somewhat recovered, although it's taken a while for aviation fuel to get up to the same level, which is why it's slightly depressed still. This going over the top is gas total. And you can see this is now huge, unsurprisingly, hugely associated with the seasons. So this spike here, if you remember, it was the beast from the east back in 2018 when it was absolutely freezing all the way to March. And the gas usage, maybe if you remember, we were very, very close to running out of gas. And in fact, our gas had to be pumped in from Norway last minute in order to meet the gas demand in the UK. Okay, so often when people, this is just to say really that often when people talk about how to go green with energy, they often mean electricity generation, but actually that's really not even half the story. Okay, so there are only 3 ways to solve the problem. One is a demand reduction or demand side balancing, and things like making, trying to turn down your heating by 1 degree and all of those kind of things. So that will help. If we're going to put more renewables with their intermittency online, then we will need to think about how to fill in the gaps. And so the only other ways of doing that are either massive overcapacity or huge energy storage, or some combination of the two. I'll go through those in order. Okay, so for demand reduction or demand side balance, so there is some scope for this. It's been politically a bit of a hot potato. There is some scope for this by encouraging people to switch off in times of high demand. For example, There was some successful trials with Octopus Energy last winter where you could sign up, and if you were on Octopus Energy, and you could get paid some nominal amount not to switch your oven on between the hours of 4 and 6 in the evening. And smart meters could theoretically help with this. And the markets do already now, because the energy prices are so outlandish, markets do now encourage this, but there's a high upfront cost. And I'm just showing this graph I've just taken off. This is yesterday at my house. So we had a slightly dull morning. This is our solar panels working. And then after about lunchtime, suddenly the sun came out and we got plenty of power, and that then tailed off. And you can see that it's obviously very intermittent. Meanwhile, this blue line is we've got some batteries, and that's how we smooth it over. So this is one of these rare days, I have to say, when we didn't draw from the grid at all yesterday. We were entirely powered by our solar panels, including charging up our car a little bit as well. That's pretty unusual. But so there is some scope for that. This system, I've now calculated, will pay itself back after about 7 or 8 years, even at today's energy prices. So it's not, you're not going to make a killing with this this kind of system on your house, but it's very pleasing. And it's also an absolute requirement that if you have the system, you have to show everyone, which is why it's in this lecture. Okay, overcapacity. So there are some things in our favor. So we don't have to fill in necessarily all of this graph. And there's some reasons for that. So if we were to electrify our heating system and go for heat pumps in a big way, just as an aside, there are problems with all of these things. But anyway, if we were, heat pumps could bring the energy demand for heating down by a factor of 3. And that's because if you use a heat pump, then you get 3 times as much heat out as the electricity value you put in. And the reason for that is entropy. You're going from something essentially very ordered in electricity, something disordered in low-grade heat. So you can win on that front. So we could reduce these humps by a factor of 3, which is brilliant. Secondly, if we were thinking about transport, say everyone went to battery electric vehicles. It's unlikely, but plausible, I guess. They're 90% efficient, as opposed to internal combustion engines, which are less than, well, around 40% or less than 40%. So that helps. So all in, electrification could reduce our energy usage by a factor of 2. That means if we had perfect energy storage, we could store as much energy as we wanted, we would need a minimum scale up of renewables of a factor of 7 in this country. It's not a factor of 1,000, but it's still a big factor. And that's just for status quo. So what about solar? So even in the UK, there is a lot of solar energy. Well, it did feel like that today, actually. It felt very nice, but might not feel like that a lot of the time. If we could magically pay 10% of the UK's land area with solar panels, and I just again, as a caveat, I'm not proposing that this should be done. But as an example, that would be on average more than enough energy for everything we need, roughly 15 terawatt hours per day. So roughly we require 6 terawatt hours per day as a kind of flat baseline as a country. Unfortunately, over winter, even 10% of the UK's land area with solar panels would not be enough. And I've got this image here taken from David Mackay's brilliant book, Sustainable Energy Without the Hot Air, which was published, I think, in 2008, 2009. But it's still very relevant. Some of it's outdated now, but this isn't. This is the instant solar flux. And you can see it changes by a factor of 9 times from summer to winter in Edinburgh, and a bit less than that in London, but still a huge factor. So we'd need really heavy long-term storage for that kind of that kind of scenario. And I've just said here, he says here in his book, and this is just another aside really to say, even brilliant people can't predict the future. And he certainly was a brilliant person. Fantasy time, solar farming, he claims there's no way this could plausibly happen because of solar prices in 2008. Well, I just took a little, went on Google Maps today, and this is just near me, and I've zoomed in. There are actually quite a few of these. Maybe just in between where I live in Abingdon and where the Rutherford-Appleton laboratories are, and you get on the satellite images, you can see these vast arrays of solar panels and solar power stations already opened up. And that's because the price of solar energy, solar photovoltaic modules has gone down on an exponential basis. So it's really been halving over the course of every 8 to 10 years. Now, David Mackay wrote around here, so you can see why you'd think it was flattened out by that stage. That was not reckoning with China investing heavily into these systems. And as another aside, actually, on that, solar panels are so cheap that even someone like Henry Snaith, who's a professor of physics at Oxford, has come up with some really clever new photovoltaic technology. He's proposing, well, certainly was a few years back, was proposing hybridization of his technology with current technology. It's actually cheaper just to buy solar panels than it is to get all the beautiful glassware that you'd need to make his own solar panels. You might as well put his technology on top to make them more efficient. That's how cheap they've become. What about wind? We're blessed with lots of wind in this country, especially in Scotland. I don't think there is plausibly enough wind energy in the United Kingdom. If we covered 10% of our land with wind turbines, then we could reach a figure of 1.5 terawatt hours per day, which could just about cover electricity generation, again, with perfect energy storage filling in the gaps. Offshore wind has potential. It's very difficult to estimate this potential, or at least I find it very difficult to estimate, but maybe a further 1 to 5 terawatt hours per day. And just to give you an idea of scale, this is Dogger Bank, which is absolutely massive wind farm installation. They're going up in, at the moment, 3 sections. Each one of these is 1.2 gigawatts, which translates to around 1.5% of the grid. And if you see the size of these, and this is the size of the countryside, you see the scale of the issue here. And also these power lines that bring them in, extremely expensive, prohibitively so for new installations, in fact. You might have seen a headline recently whereby new renewable installations have been given estimates of up to 15 years for National Grid to connect them. Okay. So what about energy storage then? What are the options? Batteries, like I have in my house, 19 kilowatt hours of battery. Maybe pumped hydro. That's this little, I think, blue slither you can see. Or hydrogen, or are there any others? So broadly speaking, there are 4 ways in which energy is stored. There's physical ways, electrochemical, chemical, and nuclear. And I've already said I'm not going to talk about nuclear, but it is an extremely important part of the overall picture. And I've slightly taken some license here because it's not exactly true, but essentially energy density goes up as you go down this list. It's not a very helpful arrow. And reversibility is easier at the top. And electrochemical actually is the easiest because you just charge and discharge your battery. And just to note, whenever you're storing lots of energy that has the capacity to discharge quickly, i.e. high power, then there will be safety issues to overcome. So for electrochemical systems, for example, lithium-ion battery fires, you can't put them out. For chemical energy systems, gas explosions, nuclear, actually, by far the safest of the lot, really. Despite its, I think if you took the general perception of the public, it would probably be the other way around. Energy storage means the ability to transport energy over time, but ideally, we'd like to be able to transport it over location as well, without relying on the grid, or upsizing our grid by a factor of 3 or 4. Okay, so I'm going to go through these in turn. Physical ways to store energy. The big one on the UK grid is this idea of pumped hydro, and that is simply pumping water uphill. And the sites are in Wales and in Scotland. This is the Festiniog site in Wales. Possibly this is the upper reservoir. So you have to have an upper reservoir and a lower reservoir. And when the energy is coming in and it's not needed, then you pump the water uphill. And then when it is needed, back down the hill it goes through a generator. And roughly you get a 75% efficiency, or at least that's what De Norway, which is the largest one of these installations in the UK, states. And there's a current capacity on the UK grid of 0.027 terawatt hours, which is in fact a very large number, but in the context of the grid, it's 2.7% of the grid, if you were to do it once per day. So it is not a huge amount. It's certainly not enough for anything more than a few hours storage. And that is how they're being used at the moment, on multiple times per day. Other possibilities that are not on the grid at the moment are things like compressed air energy storage, where you have a huge cavern underground, like an old mine or something, and then you compress the air. And then when you have excess power, you compress the air. And when you want the power back, you let the air decompress and drive a generator. And it's the same kind of idea with liquid air energy storage, which is more energy dense. You use the fact that if you can condense air into a liquid using energy, excess energy, then when it boils off, you get an expansion of about 600-fold in the volume, and that drives the generator. These are all on the kind of pilot stage of trials at the moment. Okay, electrochemical. I think the lithium-ion battery must have been one of the most society-defining inventions of the last 50 years, I would say. And there's certainly a lot of battery storage going on. There's UK's added 800 megawatt hours battery energy storage onto the grid last year. That's an awful lot of batteries. But in fact, it's a very, very small amount of what's needed for storage on the grid. And in fact, you can see that down there. It's 0.026 terawatt hours. It's roughly the same as pumped hydro, a very small sliver. And it was originally for fast frequency response, which was this, where the national grid would see that the frequency was going down below 50 hertz and would pay huge prices for any energy, any power, sorry, that could be injected into the grid at that point to stop them from having to shut things down. And pioneered by EDF and others, put on these massive battery packs on the side of power stations, and they would use those to meet that demand. As a result of which, fast frequency response prices crashed, and now it's used for arbitrage, which is over a few hours, where you try and buy the electricity when it's cheaper, and there's a whole trading system that goes on there. It is extremely unlikely that batteries will be used on a multi-day timescale. I know of no one who's claiming that that's going to be the case. They're far too expensive, and they're just not scale upable enough. Having said that, battery electric vehicles are now picking up pace. So they're 15% of new car registrations as of April 2023. And they seem to be, that presents problems for the grid being able to cope with that kind of demand. But that's certainly one way of filling in some of the energy storage on the transport side of things. And there's also this possibility of flow batteries. If you don't know what a flow battery is, so a normal battery, the energy is stored in the electrodes. So you have 2 electrodes and some kind of separator, and then when you discharge, ions, metal ions, lithium ions, move from one electrode to the other, and you get energy out, or power out, energy out. And the reverse happens with charging. With flow batteries, it's different. The charge is actually stored in the electrolyte itself. And you have 2 separate electrolytes separated by a membrane. And the idea behind that is all you need is 2 massive vats of electrolyte. So it's very clever technology. It's unfortunately very expensive, but in theory it could be scaled up to a huge amount. Okay. Oh yes, this is an image. This is an image, by the way, of Pillsbrook battery storage facility. And if you cast your mind back to that image of Dogger Bank and those power lines coming in, this is on one of those power lines coming into Yorkshire, and it gives you 200 megawatt hours of storage, which is a very small amount even of the wind energy coming in to that site, but it's still enough to rate it as the biggest battery installation in Europe. Okay, chemical. We already have huge chemical energy storage in this country. So I've said wood pellets here are in fact a form of chemical energy storage, because as a chemist myself, we claim all of biology as our own. So Drax Power Station up in Yorkshire has 4 huge domes, of which there are 2 pictured here, and they can be filled with 80,000 tons of wood pellets each. That's enough for around 1 terawatt hour of electricity. So that's about enough to, theoretically, if you could get the power out, that would be enough to do the grid for a day. It's actually 14 days with Drax running at full power. So already, once you move to chemical energy storage, we're starting to get into the kind of ballpark that we might be thinking about. Okay, we already have a way of storing energy on the grid, and it's called natural gas. So this is the gas to power stations over the same course of time that I showed the previous graph. And the reason why it's going up and down so much is because it's adjusting for wind and solar fluctuations. So what happens is when it's very windy and it's very sunny, gas-powered power stations are switched off. And when it's not, they're switched on. And it's as simple as that. All of the leeway in the system is given by gas. And you can see you don't have to go increase our solar and wind production by very much of an extra factor before this is going to start becoming a big problem. As soon as you can't go below 0 for gas-fired power. And just to give you an idea of how large the gas storage is, so natural gas storage is around 10,000 times the greater energy, 10,000 times greater energy than batteries and pumped hydro. So this is slightly unfair because batteries and pumped hydro are really only for short term, so they use multiple times, whereas natural gas storage might be used over the course of several days. Now, this graph is a little bit busy, but this kind of blue curve is the total liquefied natural gas, and compressed gas storage in this country. And you can see it's gone down really substantially. And that was largely down to the closure of the Rough storage facility back in 2018. Which I'll talk about a bit now. So the Rough facility alone, when it was at full capacity, could hold up to 30 terawatt hours of gas at full capacity, which was a huge amount. At the moment, the UK has 9 days of capacity for natural gas, which is a very large amount of energy. But if you compare it to Europe, so Germany has roughly 89 days, France has 103 days, and the Netherlands has 123 days. Italy has maybe even more than a year. They have huge amounts of storage. The UK really lives very much on a just-in-time logistics kind of delivery system for our energy. So the Rough gas storage facility was closed in 2018, at which point I think everyone tore their hair out, because it was a real example of short-term profits being maximized over longer-term energy security considerations. And sure enough, of course, come the crisis last winter, they kind of moved heaven and earth to try and reopen some of it. And 20% of the capacity has now been reopened, or is in the process of being reopened, which will, in one fell swoop, will add 50% extra energy storage into our natural gas network. Kind of extraordinary how large it is. Okay, and just say pretty much all of our transport is chemical energy storage. It's via carbonaceous chemical energy, so diesel for trains, large vehicles, some car transport, petrol, kerosene for all of our aviation. I haven't shown it here, but aviation is roughly on the order of half a terawatt hour per day. So roughly half the grid demand just for flying planes in and out of this country. Okay, so what about hydrogen? There's a kind of hydrogen virtuous circle, as it's called, where you start off with water. You take some renewable energy, you split apart the water with electrolysis, which we probably all did at school, with a couple of electrodes, a bit of salt in the water, and connected up to a battery. And Bob's your uncle, you can make some hydrogen and oxygen. And then that hydrogen theoretically can be stored. And then all hydrogen cycles seem to have a fuel cell at the end of it, which will create electricity and give you back your water. Hydrogen can be used for other things, not least for burning. It's very effective at being burned, rather too effective, you might say, given how well it leaks. This is Stephen Chu. He was Barack Obama's, well, he's a Nobel laureate, and he was Barack Obama's energy secretary. And he, in another thing of being unfair to people, back in 2012, he said there were 4 miracles to make hydrogen work. He said one miracle is you have to make hydrogen, and that's not easy. Electrolysis has not been scaled up. Then number 2, you have to store the hydrogen, and that's not easy. Number 3, you transport the hydrogen, and that's not really done. And then number 4, using the hydrogen, fuel cells haven't been scaled up. And then his quip was, 4 miracles sounds like too many to me. 3 miracles are all that's needed to make a saint. So let's go through these 4 miracles and see if this is, if the hydrogen economy is in any way plausible. So number 1, making hydrogen. The vast majority of hydrogen is made from chemical processes. Steam methane reforming. That's methane, natural gas, and water, and heat them up with a catalyst, and you get hydrogen and carbon dioxide. That is by far the biggest way of making hydrogen for chemical industry. Currently, electrolyzers are at 8 gigawatts per year manufacturing capacity. Cast your mind back and think that roughly we need 1 terawatt hour per day just for the grid. We are orders of magnitude off for electrolyzers. Having said that, it really, really, really has to be done. Number two, storing hydrogen. Hydrogen is very difficult to store, which is well, not ironic, but it's certainly very annoying, since we're using it theoretically to store energy. So it's a way of storing energy, but it is itself very difficult to store. So one of the really the only viable ways to scale up the storage of hydrogen in something feasible is to use salt caverns. And that's a picture from Engie.com, who are trying to press ahead with this technology. These vast caverns you can create underground by injecting water into salt deposits, and then to create brine, and then pumping that brine out, and you get these huge salt caverns. Currently, there are only 4 salt caverns storing hydrogen in the world, and they're used for they're all used for refineries, oil refineries. But the Rough facility, which I mentioned earlier on, is being converted partially to hydrogen. So, and we have some possible salt caverns up in the northeast. So it is possibly, I mean, it's probably the most feasible way of storing hydrogen in this country, if you're going to store it as a gas. I've just got this figure down from, this is from a report, the Royal Society, that I contributed to. I think this might be my graph. In fact, I'm sure it's my graph. And just to give you an idea of the energy density, so that's the energy per unit volume of different fuels. So the carbonaceous fuels up here, like diesel and petrol, are very high. But anything without carbon, these green ones, ammonia and hydrogen, they're much lower. But just bear in mind, this blue dot is compressed natural gas when it's in the Rough facility. So it's not that far off. It's certainly not that far off ammonia, and it's not that far off hydrogen. We're not orders of magnitude out. We're maybe a factor of 2 or 3 out. Okay, thirdly, transporting hydrogen. Hydrogen is normally fleeting when it's in usage. So oil refineries use hydrogen, and fertilizer plants use hydrogen. There's very few ways of transporting hydrogen over very long distances. Hydrogen is used in pipelines when it comes from one chemical industry normally across the side of an industrial complex to the other. So, for example, the chlor-alkali process produces hydrogen as a byproduct, and that's often used in refineries. I've seen one proposal for a hydrogen ship. This is Kawasaki, Japanese country, and they're proposing this, to give you an idea of scale, this is their proposal, 350-meter long hydrogen ship that can carry 10,000 tons of hydrogen, which is an extraordinarily large amount, and they would be proposing to carry it as a liquid. Just to give you an idea, hydrogen, in order to be a liquid, has to be at minus 230 degrees Celsius. There's all sorts of clever insulation that has to go on with these spheres. This ship, I think, as long as I've been working in energy storage, this ship has been proposed. I think they've now had some kind of approval from the Japanese government that they can go ahead and build it. But there's, as far as I know, no plans to build a fleet. But having said that, if they do build it, that's a third of a terawatt hour, a third of a day's grid usage of the UK would be stored just in this ship. It gives you an idea of why hydrogen is being taken very seriously. The UK gas grid is slowly updating to hydrogen feasible piping. If they've not come around and dug it up near you, they probably will do in the next few years. Certainly happening around our way. Very few big hydrogen projects are planning to transport their hydrogen by ship, by which I mean there's only one, and I'm not even sure if they are going to do it. Gas pipelines are really the only viable way of transporting hydrogen in its elemental form, I think. So RWE states that they claim that over 400 kilometers you want to transport electricity, it's cheaper to use hydrogen pipeline than a grid connection, even with the concomitant inefficiencies of converting to the hydrogen and then converting back to electricity at the end. Okay, finally, using hydrogen. Hydrogen for car transportation or heavy vehicles are definitely a possibility. The hydrogen refueling infrastructure is still not good. We have fewer hydrogen refueling stations in this country now than we did 5 years ago. And safety cases are still being made. This is a picture. There are about 300 hydrogen refueling stations on the planet, and one of them has exploded, which I would suggest is not a very good safety ratio so far. This is in Norway as well, a country not exactly known for shoddy engineering practices. The reason why this hydrogen refueling station exploded was because the hydrogen is compressed to 900 times the atmospheric pressure. So 450 times your, well, roughly 450 times your the pressure of your car tire. And unsurprisingly, if you get a very, very tiny leak, the hydrogen shoots out and it heats up. Most gases, when they expand very rapidly, cool down. Hydrogen barely does at all, and the friction then caused an explosion to happen, and up it went in flames. And now Hydrogen were fined $3 million for this safety incident. Fortunately, no one was harmed. So there's still a way to go on safety cases for spilling your car up. In principle, hydrogen can be used in turbines and combustion engines. It burns very rapidly. Fuel cells are still nascent really in technology, but they're rapidly growing, but from a very small baseline. Okay, okay, anything else? Because now towards the end of the lecture, I'm going to talk about what I work on. And that's the use of ammonia as a possible alternative to hydrogen, or as perhaps a better way of putting it, a way of enabling the hydrogen economy. So a modification to that hydrogen cycle means we can create an ammonia cycle. This image is courtesy of my boss, Professor Paul David. And if you start off with water, same idea, you make hydrogen from water splitting, hydrogen and oxygen. And then rather than storing the hydrogen, you say, well, what's a better way of storing hydrogen? We can take nitrogen, which comes out of the air, and combine it with the hydrogen to form ammonia. Ammonia is relatively straightforward to store and to transport, as I'll go through in a moment. And then when you want to, you can decompose the ammonia to give you back your hydrogen. You don't actually have to decompose all the way. Ammonia itself will burn after some decomposition as well. So it's a kind of small modification, and the only outputs, again, are what you put in, which is water energy and air, and the outputs are air, water, and energy. When Fritz Haber came up with the Haber process for making ammonia, called it Brot von Luft, bred from air, because of its importance for the fertilizer industry. Well, it was the fertilizer industry. But this way we're saying we can maybe get energy from water and air, or energy storage from water and air. And just to do a little bit of chemistry, nitrogen molecule, if you remember back from kind of school level chemistry, it has a triple bond, and that basically partially makes up for the formation of two carbon-oxygen double bonds that form carbon dioxide. It's not quite the same, but it does start to make up for it, which is why ammonia has such a high energy density. Okay, so I'm going to go through these four miracles again, making hydrogen. So ammonia is currently synthesized from nitrogen and hydrogen via steam methane reforming. It's done on a 200 megaton scale globally. I know I'm talking globally now. This equates to 1.5% of global greenhouse gas emissions. So certainly not an insignificant portion. And that's around 960 terawatt hours per year of energy. So more than enough to power the grid, and almost enough to power the entirety of the UK for a year. We already have to greenify or decarbonize ammonia for the fertilizer industry. So that's already happening. Storing hydrogen, it might seem incredible, or at least it does to me intuitively, but liquid ammonia has 70% more hydrogen per unit volume than liquid hydrogen. So even though you've made a liquid of hydrogen, it's so bad at being close to itself that it's better to combine it with a nitrogen, and then it packs much more efficiently. Liquid ammonia is, well, ammonia is liquid at room temperature and 10 bar. That's roughly the pressure of my bike tire if I haven't fallen off. And as I said before, hydrogen has to be below minus 240 degrees Celsius. It doesn't matter how much you compress it. And a 50,000 ton tank of ammonia, of which there are two, bought in Qatar, and 30,000 ton tanks of ammonia are fairly standard, large but standard. A 50,000 ton tank of ammonia is 0.24, roughly a quarter of a terawatt hour of stored energy. So again, you can imagine having somewhere between 4 and 8 of those, and that would, in theory, be able to power your grid. Now we're starting to talk about volumes that make sense without having to cover over huge amounts of the country. Oh, yeah, there we go. Just as a reminder, the energy density of liquid ammonia, whether you have it at room temperature or refrigerated, is much higher even than any hydrogen, and certainly much higher than lithium batteries. And strangely enough, it's higher than compressed natural gas as well. Okay, transporting hydrogen or transporting ammonia. Ammonia is one of the most shipped chemicals globally. About 20 million tons of it every year. So roughly 10 terawatt hours of ammonia is shipped every year. And this is where it's shipped to and from, this kind of heat map of the ports and the ships. So the kind of green and yellow and red lines. This is where all the ships go to and from. And you'll see that often they're associated with large energy producers like the Middle East, and Texas over here, and Florida, and they go all the way over to Europe, and basically any major port will normally have some kind of ammonia feed line. It's such a shipped chemical, and that's because it's a fertilizer. So every country needs fertilizers. Lots of green hydrogen projects that are announced. When you look in the small print, so for example, there's a very large green hydrogen project, multi-gigawatts going on in the west of Australia. And you look in the small print of how they're going to transport the hydrogen from the middle of nowhere in Australia to anywhere around the world. And they're going to do it via ammonia because that's really the only viable option. They're using hydrogen. So I said already, you could potentially decompose all of the ammonia into hydrogen and nitrogen. And that is what lots of people want to happen. I think it's fair to say anyone on the decomposition of anyone with any kind of expertise in decomposition of ammonia thinks that's a bad idea. So hence why I've said partial decomposition is probably better. So ammonia itself at 100% is actually very surprisingly difficult to burn. It has a very low flame speed and high ignition temperature. If you mix it with some hydrogen, hydrogen has a very fast flame speed and very low ignition temperature. And if you mix it, you actually get a lovely mixture, about 30%. You get the kind of best of both worlds. And the marine long distance shipping looks to be the early moving sector on this. So this is an image from Man Energy Solutions. Man Energy Solutions make, I think they have an 80% share of the long distance 2-stroke marine engine market. So they're a huge player. The size of this engine, this 2-stroke engine, by the way, you can see the railings. It's where people stand. I mean, it is utterly huge. I know people attending this talk have much more expertise in these systems than I do. But these things are massive. Man Energy Solutions are trying to make all of their new engines compatible be co-fired with ammonia, because that's one of the only solutions they see going forwards. Okay, I am aware that I'm running out of time, so I've spent all of that time setting the scene. But don't worry, I'm not going to talk for the same amount of time about this kind of things I've done. In this scenario, you'll be relieved to know. So I say I work at STFC, and we've developed world-leading. Everything's world-leading, is it? You could be world-leading at being very bad, I guess, but I think it's genuinely world-leading. World-leading ammonia decomposition catalysts, and the good thing about them, particularly, are they're based on non-precious metal systems. So ruthenium, really the only things you need to know here is, the further left you move these kind of S plots, the better, the temperature, better conversion. And ruthenium is this cyan-colored line. That's the kind of state of the art. There's only 15 tons of ruthenium produced every year. It's a byproduct of platinum mining. It's probably not very scale-upable. These very simple systems, like sodium and lithium-based systems, end up actually being more active than even ruthenium at about 1,000th of the cost in terms of raw materials. And coming back full circle, really, thanks to the ICIS neutron source, we've been able to do fundamental work to find out exactly how these catalysts work. And I'm going to scale with some data from the ICIS neutron source because I felt like I should. Don't worry if you don't understand these things, but neutrons are very penetrating, which is excellent if you're in a neutron facility and you want to use them to do science with. It's not excellent if you're next to a nuclear reactor without any shielding. But neutrons are very penetrating, and as a result, we're actually able to put the catalysts, whilst they're working with flowing ammonia over the top of them, into the neutron beam and watch how the structure evolves as we change the gases. And all you really need to know from here is you can see when you change flows and temperatures and things like that, suddenly the structure of these change. And we can see that happening in real time. And that was very fundamental work. But we were always hoping that it would have some practical application. And in turn, over the last year or so, that's enabled the formation of a spin-out company, which I think is going to up. Oh no, well, I'll come back to that in a moment. Oh yes, I was coming back full circle to ICIS. So the difference with this photo is actually out of date. And the reason it's out of date is because almost all of the roofs, the big roofs you can see in the picture, are now covered with solar panels, which is brilliant, but it's still not anywhere near enough to run ICIS. And in the background here, you can possibly see a little white stick. That's actually a wind turbine. You might be able to see the three ends of the wind turbine blade there. And behind the trees, there are about 4 containers, and there's a little green ammonia plant. It takes wind energy in, it splits off hydrogen and oxygen from water, takes some nitrogen from the air and makes green ammonia at a very, very small scale. It's being upscaled at the moment. And the idea is to provide flexibility. So the moment your ammonia plants, your big ammonia plants, chemical industry ammonia plants, they typically run for a few years, and then they're shut down over the course of a week, and they're started up over the course of a week. Our colleagues in the technology division at STFC are now proposing to run this up and down within half an hour. So that's the kind of research that's going on here, from the very fundamental all the way up to the very practical. Okay, let me talk about my spin out very briefly. This is the last slide or two, so don't worry. Created a spin out, Sunbourne Systems. It turns out that decomposing ammonia by 30% into a hydrogen and nitrogen ammonia mixture means that you have the possibility to retrofit combustion engines. And the reason for that is because that mixture demands the same rate of airflow through your combustion engine as kerosene, for example, does. This means that there's a possibility to retrofit them. You don't have to resize components. All you would end up with is about 40 to 50% of the range that you get with, say, jet fuel. So no stranded assets, and as a bonus, you get more out of your ammonia fuel by using the waste heat from your engine to help decompose your ammonia. In this little diagram, that's what's happening. There's a heat exchanger here, and the heat exchangers we're using are from a company called Reaction Engines Limited, and it's a joint venture between STFC and Reaction Engines. They have these world-leading heat exchangers that are used in Formula One cars and designed for rocket engines, and we have the catalyst, and we're combining the two of them to create something that could potentially power combustion engines from ammonia. So originally we designed for aviation because Reaction Engines are a rocket company, but we think marine is probably going to be the first mover on this. I haven't quite realized just how conservative and lacking in imagination aviation companies are, which I guess is fair enough because they've got to keep their planes going. You can't have the engine just suddenly fail on a plane in the way that possibly you could on a ship, even though that's not good either. Okay, so brief. This is the last slide. Conclusions. Don't be fooled. The task is monumental. It is doable, but we mustn't let the best be the enemy of the good. And quite often you'll hear things like, I guess the most green of the major newspapers, The Guardian, will chuck out things like saying just ridiculous things, saying, "Oh, we don't need nuclear because solar energy is so much cheaper." Someone with no understanding has written that. We will need lots of different solutions. I've said and lots of different solutions, by which I mean we will need a large amount of every different solution. So we will need large amounts of batteries. We will need large amounts of hydrogen or ammonia. We will need large amounts of solar. We will need large amounts of wind. We will need large amounts of everything. A form of a hydrogen economy is probably coming, I think. Certainly, the mood is going that way. But it will be a mixture of technologies, not one technology to rule them all. And I expect ammonia to be a very large part of that, especially transporting hydrogen from areas with an abundance of energy, like the Middle East and Morocco, to areas like the UK where there isn't really an abundance. And just to acknowledge the colleagues at STFC who I've worked with for the last 10 years on this, and to thank you very much for your attention. If you have been paying attention, I can't see. I assume people are still there. But I'm done. I don't know who's chairing now at this point.
Well, I think I am in the absence of Tom.
Can you hear me,
Yeah.
John? Okay, let me turn off my other source. So we go back to one. My sincere apologies for my technical failure. Can you still hear me?
We can still hear you.
Great. Yeah, Tom, thank you very much indeed. Wonderful. I really think it was a really holistic approach. Goodness, all the avenues and, as you say, monumental task before us. I'm really interested in ammonia as a thing, but just one quick question. We don't get too technical, but you can put lanthanum and nickel as a method to store hydrogen, because within the atomic structure, hydrogen is very readily absorbed in immense volume, but it is very, very heavy. So you'd have to do it on land based. You couldn't sort of use it as a method to move ships and trains and things around. So I just throw that in there because you didn't mention it. That's all.
Yeah, no, you're right. There are several technologies I didn't mention, and you're right. Of the hydrogen storage technologies, lanthanum nickel is actually a nice one. I suppose the vast majority of these solid hydride technologies, which are not reversible in the slightest, but lanthanum nickel is a good one. And you're right. My suspicion is that salt caverns will be the way people go if they want to store large amounts of hydrogen. At the moment, that seems to be, and I wonder whether I haven't actually done the scale up calculations for how much lanthanum you would need. But I wonder if partly the reason is because that's what big oil and gas are used to. So it's technology they're very happy with. And at some point, there's a whole load of expertise in the oil and gas industry, which the world needs to leverage if we're going to decarbonize. That's my suspicion. But yes, you're quite right. I didn't. There are other technologies that I didn't mention as well. Oh, you're muted, Tom. Sorry.
Can I just,
Sorry.
Alan, can I just make one further comment on Tom's comment, which is that actually hydrogen storage has been used in sea applications for submarines for quite some years, simply to power electric motors for silent running on non-nuclear submarines. So actually, the sea use of such things for storing hydrogen is actually already a known technology. One other little question I have, which was just there was this thing about the heat pumps being producing three times as much energy as you put in with power. Is that actually before or after the energy cost of the equipment manufacturer?
Yeah, so no, it's operating only. But it will.
Have we any idea how much the equipment cost?
In terms of energy costs, no, I don't. It's not particularly. I mean, they are expensive if anyone's tried to buy one, of course. But I think that's probably because of a scale issue. So no, I don't have an overall energy balance for that.
Yeah.
I don't. My suspicion is that the grid won't be able to be scaled up enough to cope with everyone going onto heat pumps. That's my suspicion at the moment. Unless small modular nuclear or something that you can really go for in a short amount of time gets put on the grid. I don't see that the infrastructure. I mean, we'd be looking at tripling the grid, at least just to do that. Maybe quadrupling if you also have battery electric vehicles. I think that's probably a prohibitively large expense. I'm actually going to ask the question straight back because I didn't know about the submarines at all. I presume you didn't fill up with hydrogen to start with, or was it just used for a few hours running at a time?
Well, it was actually a German submarines, diesel submarines, but for silent running, obviously had electric motors, and that power was provided by hydrogen fuel cells, with the hydrogen stored in significant tonnage batteries, if you like, for the hydrogen. My recollection was that the metal stored something like 1% of its weight as hydrogen.
Okay, yes, so
which actually is quite a lot of hydrogen when you
yeah.
But it's certainly been well used. I mean, it's well known in the sort of marine or military marine world. So I was just intrigued when you was talking about powering ships with ammonia when needing some hydrogen. Whether that, rather than carting around liquid hydrogen, this was a way which might provide enough for such propulsion units. Anyway.
I seem to remember, Alan, it was your sister company in Germany, JFA, who did this. And I think it was just because of the silence that they were doing it. It wasn't for any other reason.
Yeah, it was because, I mean, the submarines run silent on electric power. rather than diesel. That was the really main thing. Actually, the biggest producer of it was the German company's main competitor in Austria, which was Treibacher.
Yeah. John, I think you better carry on hosting if you don't mind, because it thinks I'm driving. I've got you up on my iPhone and it thinks I'm driving, so it keeps stopping my video. So you might be able to hear me, but I can't see anyone, I'm afraid.
Well, I think we're getting on a bit. And Roger, come on.
First of all, Tom, let me say I think that was a very nice tour around all the possible things, way of doing the storage. But perhaps the few comments I'd like to make was, one said, towards the end of your talk, you said, if we're going to decarbonize, I think there's no alternative. We're going to have to decarbonize, right? It's not an if. We haven't got the chance to not make that decision. So something's got to happen. The second thing that I want to comment on is a nice description of the energy sources and things like this. And of course, what I've been saying to people of recent times is, at the moment, the energy that we use in the world, the global energy, and I think you will have something similar to this in your plots, that it's an enormous amount of energy, and 75% of it is now derived from fossil fuels, right, at this moment in the world. And we've accumulated that, got to that position over about 100 years, right? So now what we're proposing we've got to do, and this is why it's urgent, is we've got to try to change that 75% of the whole of the energy system, as you're careful, in 20 years. That's the sort of scale of the task, and we don't have the answers yet, as you were quite clearly and eloquently telling us. And we've got lots of good guides and lots of good ideas, but in 20 years from now, we've got to change that whole global energy system. This is a real task. I mean, and you know, like you, there's lots of good ideas around, as you were saying, and I think some of those are going to come through, and they're going to come through, thankfully, will come through comparatively quickly. One question I would have for you, though, is ammonia. It sounds very attractive, but I've also heard comments that people are very nervous about the large quantities of ammonia being shipped around, or if you had accidents in ports where you'd have to bring the ammonia carriers into, you could cause monumental deaths rates if you had a big release of ammonia, as it's a very nasty gas when it gets, and people's lungs don't actually particularly like it. But that's one of the problems for it. But the sizes of the engines and things you were talking about, that will be solved, right? And you were saying that, I think, because, you know, think about container boats, right? 200,000 ton container ships, right? They're enormous size, right? And they can take enormous pieces of kit and new designed engines, right? So I think there's a chance, and they know they've got to change those container ships and the propulsion units for them. And the only answer, I think, really is hydrogen or is ammonia. I mean, it probably will be ammonia because of the comments that you described to us, right? So, but we've got to get on with it, and it's a good job that Maersk, I think, is starting to look now to get such a container vessel into operation. But it's a phenomenal task, right? And and we've all got to get on with it. No ifs, no times to consider. We've got to kickstart the whole activity to give at least my grandchildren a good chance. So anyway, so thank you very much. It was a very good tour de force. And by the way, I taught Bill David.
Yes, I know. He remembers you fondly. I couldn't agree more. And your perfectly right to pick me up on my misspeaking. I did not mean if, meaning you know, it's an either or choice. Just on that, you're absolutely right. Ammonia. So ammonia is transferred in ports all the time with no real problem. I think one of the biggest barriers to its usage at the moment is it's not bunkered as a fuel, and so there are no regulations over that, and so we'd have to be very careful. But in principle, it should be overcomable given the amount it's transported. For example, the refrigeration facility for the cooling at Terminal 5 at London Heathrow is ammonia. You know, large amount of ammonia stored there. It's used in the refrigeration industry all the time. It's relatively, the hazards are very well known, I think is perhaps the best way of saying it. Also on the bunkering side of things, funnily enough, it's actually the fertilizer companies that are moving first, which is not what we were expecting. But Yara, which is one of the largest fertilizer companies in the world, has got 15 bunkering barges to refuel ammonia-powered ships, and they're coming online this year. This is not the classic, oh, by 2030. They announced this last year, and they're coming online this year. There was a lot of movement in this space. I think when we go back 10 years and we went to an ammonia convention, it felt a little bit like a UFO convention. Everyone's convinced they've seen UFOs and they know everything. And there was a time to take a look at ourselves and say, are we actually quacks or cranks? But actually, it seems like part of the world has moved towards us in this regard, which then has the benefit of making us look very wise. But of course, it might. there are problems to overcome still, I'm sure. But yes, yeah.
It's reassuring to know those examples where there's a lot of it. But you know, people do also worry about tankers and things like this colliding or hitting and blocking the Suez Canal and wrecking things like this. And it's so, I mean, I think there's a big safety issue about it, as far as I understand. And there are big ports which have got tons and tons of boats, big boats coming in and out of, and worried, I believe, about accidents that cause a leakage when you've got that much more on the move, because there's going to be a lot more ammonia on the move in your world than there is now, even, right?
Yeah. So
interesting.
I have a feeling, since you two live close to each other, you should continue this conversation outside, because we're coming to the end. Are there any final questions at all? I suddenly see Kim has come into view. Hello, Kim. Well, in the true tradition of the head of ISIS, when I was running the Rutherford lab, a chap called Andrew Taylor, and after every talk I gave, he said, 8 out of 10, John. And so I think I'm going to award Tom 8 out of 10, because that's the highest score you're allowed to give. And Tom, on behalf of everybody, and I'll see you this weekend to tell you where you're wrong. No, I won't. Thank you so much. I don't know if the master wants to say anything in conclusion. You do need to demote, Robin.
Yeah. No, I have now demuted. No, just say thank you very much again, Tom. Thank you. Fascinating. Some of it's clean over my head there.
Oh, I apologize. Well, thank you very much for having me.
No, thank you. And it shouldn't be for the father to thank the son, but you know, it was even Mary, our daughter, who is highly critical, has given a thumbs up. So thanks very much indeed, old chap.
All right.
And thank the rest of you for surviving until now. Goodbye, everybody. Oh,
Thanks,
hi,
everyone.
Bye. Thank you.
Good night. Good night.